Okay, coordinate covalent bonding. This is an interesting type of coordinate or covalent bond rather because in some cases a molecule can achieve a full octet, and this is very common in polyatomic ions. They are actually ionically bonded externally to another ion, but internally bonded with covalent bonds. And quite often the structure of the bonds around the central atom in a polyatomic ion is coordinate covalent bonding. So what is coordinate covalent bonding? Well, to coordinate something is to organize it, and usually when you have a coordinator, they do a lot of the work on their own, or at least they lead. Coordinate covalent bonding has one atom kind of leading the sharing of electrons, and to the extent that the electrons in the shared pair originate from that one atom. And when this happens, this is called a coordinate covalent bond. It's not a giving of electrons, it's a sharing of electrons that originated from only one of the atoms. And it's unique, and not all molecules include this type of bonding. So that's why we wanted to look at some examples here. I'll just show a little video clip here to help you see this in a little more detail.
When NH3 encounters BF3, the NH3 uses its lone pair electrons to form a coordinate covalent bond.
Okay, I've just shown here ozone and oxygen gas, both obviously they're elements. Diatomic and triatomic, different forms of oxygen. And in this case, it's pretty easy to draw the oxygen molecule. It's typical covalent bond, sharing of two electron pairs. There are four non-bonded electrons surrounding each oxygen atom, gives both oxygen atoms 8 valence electrons. No coordinate covalent bonding involved in here. The bonding capacity for oxygen is 2. And when we look at whether or not coordinate covalent bonding may be taking place, we have to look at whether or not the bonding capacity is either exceeded or, in some cases, not met. The number of bonds that this oxygen atom here, we almost really need to label them oxygen atom 1, 2, 3. You don't want to really think of at the atomic level how the oxygen atoms decide who gets to get 3 bonds and who gets to have only 1 and which one gets 2. But this works itself out probably on a very large scale, and this works. We can draw the structural formula, or in this case the Lewis structure, looking at trying to place 18 electrons in this diagram. And if we count the number of electrons, we have 6 around the first oxygen atom plus 2 for the bonded pair is 8. We have 2 more bonded pairs around the second oxygen atom, which brings us up to 10, 12. We have a non-bonded pair here on the second oxygen atom because it's 14. And the last 2 electron pairs on the third oxygen atom would bring us up to 18. So that actually works. Now, when we look at how that might happen as far as bonding, it's going to require a different explanation, because when we draw the electrons for an oxygen atom, we know that it has 6 valence electrons. All 3 have 6. They're unique in that. But they're all equivalent. So how do they bond differently? Well, in order to predict the double bond between oxygen atoms 2 and 3, we would perhaps want to redraw our diagram here and show, and this is appropriate. Sometimes we need to do this with our diagram, is just to help us see how the electron pairs can come into to being. Just reorganize your Lewis symbol a little bit. So that predicts a double bond between oxygen atoms 2 and 3. And now we have a situation where the second oxygen atom actually has a full octet. It has, both of them would have 8 valence electrons surrounding each. And we saw that in the method here that it was mentioned, if you find that you can remove an atom from the molecule and the remaining atoms have full octets, that's a very strong indication that coordinate covalent bonding is required. The other indication is that in order to form the complete molecule, we need to have 3 bonds to that central oxygen atom, and that exceeds the bonding capacity of oxygen by 1. Okay, so that means that the bonding type between the first and second oxygen atom is going to be a covalent bond, but it's be a special type called the coordinate covalent bond. In this case, the second oxygen atom has 8 electrons, so it can't receive any more from the first oxygen atom, but look at the first oxygen atom is still short too. So what would probably happen is a reshuffling of the electrons within the atom, where I'll sort of show it as I may imagine it would happen, where these 2 lone electrons would reorganize, and this pair of electrons here would coordinate to give this bond. And I've sometimes shown students that if you use a dotted line to represent a coordinate covalent bond, then you can use a little legend off to the side and indicate that that is a coordinate covalent bond. And then I understand your Lewis structure. And then if you redraw it, you would have the 2 original non-bonded pairs, and now we have a third non-bonded pair because this oxygen atom is not really contributing any electrons to the shared pair, but it's still sharing those 2 that came from the second oxygen atom. So it's a difficult type of bonding to understand, and it's going to be the most challenging for you when you're drawing structures, is to try to determine maybe in advance whether or not coordinate bonding is required, but you often just stumble upon it as being necessary to explain how a structure like ozone could exist. So we have 2 single bonds, or a double bond and a single bond to complete the structure for this molecule. We're going to look at the polyatomic ions. Maybe I'll show one, and the remainder of them you can do in class tomorrow. All right, well, in this example, phosphate. So how does the phosphate ion come into existence? There's 2 things that we have to be careful here. First of all, it has a charge, which means that 3 additional electrons have been contributed from another ion. And a question in class the other day was an interesting conversation, because the student was already thinking about where do those electrons come from, and how can they just receive additional electrons or give away additional electrons, where are they going, where are they coming from? Well, keep in mind that ionic compounds are formed between ions, and phosphate is an ion. So phosphate, although it is internally held together by covalent bonds, would be externally connected to another ion ionically by electrostatic attraction. So those 3 electrons have come from maybe an aluminum atom, or possibly 3 potassium atoms, or possibly if phosphate is formed with calcium, it could be that electrons have come from calcium atoms to produce multiple phosphate ions. Wherever they come from, that's not much of our concern right now. 3 additional electrons need to be added into the diagram. So when we start to draw the structure of this, again, bonding capacity demands that phosphorus be the central location. We can start to form bonds here, and this is pretty natural that we'll first form single bonds, and let's try to do that as much as we can. Now, at that point, look carefully at phosphorus. It now has 246 plus its non-bonded pair, 8 electrons. That's an indication that the remaining oxygen atom, in order to be linked into the molecule, has to be bonded using a coordinate bond. And as we did before, we kind of rearranged the electron structure for the final oxygen atom into 3 non-bonded pairs, and we coordinated a bond coming from the central atom. Okay, you'll see that the central atom is always involved in the coordinate bonding. So that satisfies all of the electrons required for phosphorus. The only problem is oxygen is short in this case 1 electron each. Okay, that's where the charge electrons come in. So we have to remember to add 3 additional electrons in our diagram, and we can rightly do that because we know that the formation of phosphate, this is not phosphorus tetraoxide, this is phosphate. It comes from the addition of 3 electrons. Because this is a Lewis structure, we can show all the electrons. Because it's an ion, we should, as we've done before, put a bracket around it and indicate the charge. Okay, so I really enjoy, relatively speaking, as far as things that are enjoyable. When I'm doing science, I like a challenge, and many of you probably feel the same way. I really like trying to figure out the structure of polyatomic ions because they're very dynamic. They have different types of bonding, and we also have to remember the charge. So at this point, if that's enough for you to keep going, you want to look at the other examples, B, C, and D, or you can come back and view the remaining 3 examples tomorrow night in your home time, okay? Okay, hydroxide's pretty easy. In this case, it only has one single bond, so it hasn't met its bonding capacity, but there's no need for coordinate covalent bonds. Oxygen needs to gain 2 more electrons, and it can do so with a sharing of a pair with hydrogen and an additional electron for charge, which could come from a metallic atom, whether it be group 1, group 2, group 3, that's not important. But additional electron has to be added in. That gives it its overall charge of -1. Now, the skeleton structure for bromate, this is the bromate ion in part C, is a little unusual because the central atom is actually not oxygen, although oxygen has a higher bonding capacity. So there's some interesting things that are going to happen here. We're going to definitely exceed the number of bonds to bromine, which for halogens is 1. So minimum number of bonds we need to form is 3 because there are 3 surrounding oxygen atoms. So we can now start to predict not only whether there's going to be coordinate covalent bonding, but how much of it. And in this case, the bromate ion is held together by shared electron pairs, but definitely there's going to be some coordination with that central atom. So let's remember to add the extra electron, but we can do that towards the end. As we start to pair up our electrons here, let's form a single bond here. Now again, right off there, we've satisfied the octet for bromine, which means that in order to bring in the other 2 oxygen atoms, that central bromine atom will have to coordinate the sharing of electrons with those other 2. So we're going to have to reshuffle our electrons as we did before, and that just requires a simple adjustment to our diagram. How that exactly happens on an atomic level is for us to kind of contemplate, but that gives us 3 non-bonded electron pairs where bromine will coordinate a bond to each of the oxygen atoms, which gives them their 8 electrons, 6 of their own and 2 being shared with bromine, that are spending some time in that central atom's valence orbit and some time in each of the oxygen's valence orbit. The only thing missing now is the 1 electron for the oxygen atom that had just a normal covalent bond, and that gives us the correct number for all the elements, and we have to remember the charge is -1. Okay, now when we set up the central atom here, again, very different from the other examples we looked at. Chlorine with a bonding capacity of 1 finds itself surrounded by 4 oxygen atoms to form the perchlorate polyatomic ion. Okay, we'll get to that a little bit later, but refers to an additional oxygen atom beyond the base ion. So when we name oxyanions, we'll look at that later, but the perchlorate polyatomic has 4 oxygen atoms and only a charge of -1. So we're only permitted to add an additional electron to our Lewis structure. So let's start by linking up one of the oxygen atoms to the central chlorine. That satisfies chlorine's octet, which tells us that in order to bring in those other oxygen atoms, they have to be coordinated. And as we did before, we're going to just make a simple adjustment here to the arrangement of electron pairs on the oxygen atoms surrounding, giving us 6 non-bonded electrons, and we're going to coordinate in each of these electron pairs to join up the three oxygen atoms. Again here, all the oxygen atoms have had a full octet satisfied, with the exception of the one that was actually involved a little bit more in the covalent bonding with contributing an electron. And you'll probably observe that that's pretty typical in how you at least draw the Lewis structure, that extra electron that comes in for the ion's charge from the metallic atoms is likely going to move into the valence orbit of that oxygen atom, which has an ordinary covalent bond. Difficult concepts here, and I hope these examples were helpful. The assigned exercises, as you can see, for the 3U's, I suspect the number 2 also on page 82 is some coordinate covalent bonding. So we'll see you in class.